garden. In the tropical belts of the world, from India to Ecuador, the banana is king.
Once the fruit is plucked, the plant's life cycle ends. This is the pseudostem.
Botanically, this is not a tree. It contains no wood. The banana stem is actually a collection of tightly packed leaf sheaths. It is 90% water.
But holding this water weight is a skeletal structure of incredibly strong natural polymers. Turning this biomass into high-tech fabric begins here. Not every stem qualifies. We require stems. Logistics is the first hurdle. Transporting material that is mostly water is inefficient. Speed is critical to prevent oxidation.
The raw material travels from the chaotic organic environment of the plantation to a controlled, sterile industrial ecosystem.
Welcome to the future of textile engineering. Inside this facility, biological waste will be deconstructed and rebuilt. Before we can extract the fiber, we must surgically separate the layers. This is the tuxing phase. The process begins with the bucking phase. The 12-foot stems are too unwieldy for precision machinery.
Optical sensor scanacity.
This is the tuxing station. In traditional farming, this is done by hand with a knife, a dangerous...
The machine separates the layers into two distinct categories. The outer sheaths, dark green and rich in lignin.
But as we move inward, the chemistry changes. The inner sheaths are nearly pure white.
The curved strips, known as tuxies, must be flattened to ensure the extraction blades hit every fiber evenly.
The challenge is molecular. Cellulose fibers are naturally glued together by a substance called lignin.
Automation sorts the raw material streams. We do not mix the grades. Uniformity at this stage is the only way to guarantee the tensile strength of the final thread.
The tuxies are now prepped, flattened, sorted, and fresh. They are ready for the most violent part of the process.
Next, they enter the decorticator. Here, brute force meets precision engineering to strip the flesh from the fiber.
This is the raspador. Spinning at 1,200 revolutions per minute, it generates enough kinetic energy to strip the flesh from the plant in a fraction of a second.
Safety and precision are paramount. The strips are fed into the death zone by an automated grip conveyor. If the grip is...
The science here is not cutting, it is scraping. The blades are blunt, not sharp. They rely on impact. The engineering tolerance is razor thin. The gap between the spinning blade and the bed plate is set to exactly...
The stripped pulp, rich in potassium and water, is not discarded. In this facility, it is diverted to an anaerobic...
In seconds, a solid log is transformed. What emerges is raw banana fiber. At this stage, it looks like wet horsehair. But it is covered in sap, a sticky, oxidizing fluid that turns brown if left exposed to air. High-pressure jets immediately...
Even with advanced automation, the human touch is the final arbiter. Technicians check for sheaths, tiny...
The extraction is complete, but the fiber is currently coarse and stiff. It feels more like wire than silk.
To turn this wire into wearable luxury, we must alter its molecular chemistry.
In its raw state, banana fiber is brittle. If you tried to spin this, it would snap. We need to strip away the gum.
In the past, factories used harsh acids. Here, we use a bio-cocktail. The fiber is loaded into high-pressure digesters. Once sealed, the environment inside becomes a controlled tropical storm. For 3 hours, the mixture is cooked at 95 degrees Celsius. The heat relaxes the molecular bonds.
This is enzymatic hydrolysis. The enzymes act like microscopic scissors.
The process is monitored via the liquor. As the water turns dark, it signals that the impurities have been successfully stripped from the solid matter.
The reaction must be stopped precisely. We flush the system with cold, neutral pH water to deactivate the enzymes.
The transformation is physical. The rigid wire has become banana silk. It is now soft, pliable, and ready to be engineered.
But it is saturated. Before we can align the fibers, we must remove the water weight. A centrifugal hydro extractor.
The fiber is now soft, but it retains the natural pigmentation of the plant, a dull, uneven beige.
Traditional textile mills use chlorine, a cheap, toxic bleach that harms the ecosystem. Here, we use hydrogen.
Elegant. When the peroxide degrades, it releases free oxygen radicals.
Over 60 minutes, the oxidation strips the color. The fiber reaches a whiteness index of 85, comparable to high-grade cotton.
A final hydro rinse removes any residual salts. The water exiting this tank is clean enough to be filtered.
We have a problem. Clean cellulose is naturally dry and high friction. If we sent this to the spinning machines now,
The solution is batching oil. We apply a microscopic layer of biodegradable emulsifier. This acts as a lubricant.
Rollers press this emulsion deep into the core. It ensures the fiber remains supple and reduces static charge to 0.
Now the fiber enters the thermal tunnel. Drying is not just about heat, it is about airflow. We use a radio frequency dryer.
We do not dry it completely. If bone dry, it breaks. We target exactly 12% moisture content.
The fiber is now clean, white, and dry. But structurally, it is chaos. The individual strands are crisscrossed.
The material enters the hopper feeder. This machine performs the preliminary opening, breaking large clumps into smaller.
This is the carding engine, the heart of the spinning mill. Its job is to perform a mechanical magic trick.
Inside, the main cylinder is covered in millions of microteeth, angled precisely. These teeth comb the fiber into this. It is a process of intense discipline. The fibers are combed parallel to each other. Any short, broken fiber.
The result is the web, a film of fiber so thin it is almost transparent.
But the web is too fragile to handle. It passes through a condensing trumpet, collapsing the sheet into a continuous, soft rope called a sliver.
To ensure absolute uniformity, we use the draw frame. We combine 6 slivers into one. This double.
An auto leveler scans the thickness 1,000 times per second. If it detects a variance,
The chaotic bale is now a precision-engineered sliver. It is coiled into cans, waiting for the final transformation, the twist. The sliver is too thick to spin directly. It visits the roving frame first. Here, it is drafted, stretched out. We now enter the ring frame. This is where the yarn is born. Thousands of operate in perfect unison.
the logic is simple but essential. Loose fibers have no strength, they slide apart. But by applying twist, we create friction.
The secret is this tiny component, the traveler. It flies around the steel ring at 20,000 revolutions per minute.
The speed is critical. Too slow and the yarn is soft but weak. Too fast and the tension snaps the thread.
We measure this in TPI, twist per inch. For banana fiber, we use a high twist count to lock in.
When the bobbins are full, human hands do not touch them. An auto doffer swaps thousands of spindles in under 2 minutes, keeping efficiency at maximum.
The small bobbins are combined onto large industrial cones in the winding department. But this machine does more than just wind.
It rejoins the ends not with a knot, which would cause defects in weaving, but with a blast of compressed air, tangling the fibers back together seamlessly.
The result is a cone of banana 60s yarn. Stronger than cotton, more breathable than polyester, and completely biodegradable. Before weaving, we must prepare the warp, the lengthwise threads that form the backbone of the fabric. 600 cones are...
These thousands of ends are wound under high tension onto a warp beam. If a single thread is loose, the loom will...
The loom is a violent environment. To survive the friction, the yarn is coated in size, a biodegradable starch mixture.
We enter the weaving hall. This is the loudest room in the factory. Here, hundreds of air jet looms.
Weaving is the intersection of two sets of yarn. The warp runs vertically, held under tension. The weft.
Old looms used a wooden shuttle. We use air. A concentrated blast of compressed air shoots the weft thread across the fabric width at 600 miles per hour. The harnesses lift and lower the warp threads 800 times per minute. This creates a tunnel called the shed for the wefters.
After every insertion, the reed slams forward. This is the beat up. It pushes the new thread tight against the
This is not random. An electronic dobby controls the pattern. By programming which threads lift, we can
What emerges is grayish fabric. It is raw, strong, and ready for the final stage, testing and finishing. From the chaos of the weaving hall, we move to the silence of the laboratory. Here, the fabric faces its...
First, the visual scan. An AI-powered optical system inspects every centimeter at 5,000.
Next, the tensile test. We measure the force required to rip the fabric apart. Banana fiber is naturally strong, possessing a high cellulose content that rivals linen. It withstands 600 newtons of force before failure, significantly higher than standard organic cotton. Durability is tested via the Martindale method. The fabric is rubbed continuously against wool sandpaper for 20,000 cycles. The Elmendorf tear test measures resistance to snagging. If a nail kel catches your shirt, will it rip open?
Comfort is physics. We test wicking. Because the banana fiber is a natural tubular structure.
Under the scanning electron microscope, the secret is revealed. The fiber has a central hollow channel called a lumen. Finally, color fastness. We ensure the dye has bonded molecularly with the cellulose. Even under intense friction, the color must not bleed.
The journey ends in the fabrication room. Here, we do not use scissors. Computer numerical control lasers cut.
The assembly is automated. The fabric is fed into robotic sewing units. Because the material has high tensile strength,
nothing is wasted. Remember the short fibers rejected during carding. They are not thrown away. They are...
Because of its hollow structure, the fiber is highly absorbent. This makes it a sustainable replacement for plastic-laden sanitary.
The environmental math is undeniable. Producing this fabric generates 37% less goods.
But the greatest impact is human. Farmers who once paid to dispose of rotting stems now have a second income.
And when its life is over, it leaves no trace. While synthetic polyester sits in landfills for 200 years.
From the soil to the skin and back to the soil.
This is the future of industry. We are no longer just building things, we are growing them.